Welcome back, focused learners. I am absolutely thrilled to have you here for today's explainer. If you have ever felt the downright pain of managing machine learning models at scale, well, you are in exactly the right place. Today, we're zooming in on a really powerful platform in our AI tools category, one that's designed to bring serious order to the total chaos of scaling machine learning infrastructure. That tool is Polyaxon. We're going to break down exactly what it does, how it actually works under the hood, and how it can literally transform your team's entire workflow. So get comfortable and let's jump right in. To really wrap our heads around why a platform like Polyaxon even needs to exist, we got to ask ourselves a highly relatable and frankly often painful infrastructure question. What actually happens when dozens of engineers are forced to share a single GPU cluster? If you've lived through this, you already know the answer. As machine learning teams scale up to running hundreds of experiments, they inevitably hit a very specific wall. Managing team-scale experimentation without the right underlying infrastructure, it's not just annoying, it becomes a massive, complete bottleneck for innovation.
Okay, let's dive into this. Think about the ideal state versus the reality. In a perfect world, you've got this beautifully organized environment where compute resources are shared efficiently and everyone knows exactly what's running at any given time. But the reality? It turns into the Wild West. Training scripts diverge, results become completely unreproducible, and those incredibly expensive GPU nodes, they basically morph into someone's personal, untracked sandbox. It's an absolute logistical nightmare for everyone involved.
So, to make sense of how to fix this mess, here is our roadmap for today. First, we'll look closely at the ML scaling wall. Second, we'll introduce our solution, Polyaxon. Third, we'll peek under the hood at the architecture. Fourth, we'll walk through workloads and tracking. And finally, number 5, we'll ground things by looking at deployment realities and trade-offs.
All right, part 1, the ML scaling wall. I genuinely empathize with the data scientists and DevOps pros hitting this wall, mainly because it totally sneaks up on you. You've got dozens of engineers running hundreds of experiments, and without a central tracking system, you lose any shared view of what actually ran. It becomes incredibly unclear which specific configuration produced which result. And the most dangerous symptom of all? Total, complete uncertainty around which model version is actually sitting out there in production. When you lack centralized tracking, lost configs and unreproducible results aren't just a risk, they are an absolute guarantee.
Moving right along to Section 2, Introducing Polyaxon. There is actually a way out of the Wild West. Enter Polyaxon. It's a Kubernetes-Native MLOps platform built specifically for team-scale experimentation. Right now, it's sitting on version 2.15.1 and it's open-sourced under the Apache 2.0 license. The fundamental magic here is that it deploys straight onto Kubernetes and magically turns your raw compute hardware into a shared, scheduled, and best of all, fully auditable resource. So what does it actually do? Well, it handles experiment tracking, workflow orchestration, hyperparameter tuning, and model registry management. The whole shebang. It basically manages the full machine learning lifecycle, whether you're working in the cloud, on-prem, or rocking a hybrid setup. Most importantly, it completely eliminates the guesswork by strictly tying every single experiment you run to versioned code and configurations. No more mysterious models.
Which brings us to Section 3, Architecture under the hood. Now, what's really interesting about this slide is that Polyaxon isn't just one massive, clunky block of code. It's a monorepo split across several independently maintained subcomponents. It's like a giant puzzle. Let's break it down. First, you have ML operator. When you submit a TensorFlow or PyTorch job, ML operator translates that into actual Kubernetes resources. Then there's Hopt, which is essentially the brain. It manages the core API, the queuing, and all the node allocation logic. Next up, TrackML handles the tracking side, logging your metrics, artifacts, and data lineage. Finally, Hypertune manages your hyperparameter search algorithms. This modular setup is great, but a quick heads up, if you're ever debugging a weird edge case, you absolutely need to know which of these subcomponents owns the behavior.
Section 4, Workloads, Tuning, and Tracking. And this brilliantly illustrates how all these pieces actually come together in the real world. A day in the life usually starts with a declarative YAML manifest, what they call a Polyaxon file. Just look at how clearly it specifies the container image, the training command, and resource inputs like your learning rate and epochs. By basically forcing you to define your jobs this way up front, Polyaxon ensures that every single run is documented and perfectly reproducible by design. Once that YAML file is ready, running and tracking the job is honestly seamless. First, you just use the CLI to submit the job. Hitting it with the -u flag uploads your local code, and the -l flag tails the logs so you can literally watch what's happening live. Then, inside your actual training script, you use the TraceML SDK. You use it to log specific metrics, like say your validation accuracy, and artifacts like your trained model weights. These log directly into the centralized dashboard, making them fully queryable and comparable across your entire team.
Now, when you're ready to really optimize those models, the Hypertune subcomponent steps up to the plate. You can define search spaces right there in your Polyaxon file across a whole bunch of strategies. We're talking grid search, random search, hyperband, Bayesian optimization, and even custom iterative optimization if you want to get fancy. Polyaxon will just automatically run these jobs in parallel, scaling right up to whatever concurrency limits you've mapped out for your cluster. But hey, what about interactive work? Data scientists love poking around in their notebooks, right? Well, interactive environments like Jupyter Notebooks and TensorBoard are treated as first-class citizens here. By running simple commands, these tools are launched as Kubernetes jobs managed by the platform itself. This is huge because it means even your quick interactive exploratory work is fully tracked, resource managed, and kept far away from that Wild West we talked about earlier.
And that brings us to our final part, Section 5, Deployment and Trade-offs.
Everything we've covered sounds fantastic, but let's ground this explainer in reality for a minute. Deploying Polyaxon requires some serious infrastructure chops. Actually, before you even start the steps we're looking at, you must have a running Kubernetes cluster, kubectl, and Helm ready to go. The deployment process itself means installing the CLI via pip, creating a dedicated Kubernetes namespace, adding the Helm repository, and finally, deploying your configuration using a config.yaml file.
And let me tell you, that config.yaml file is absolutely critical. If you're going into production, here's what you need to know. First, storage connections for things like S3 or Google Cloud Storage require explicit configuration right at deploy time. If you don't set those up early, jobs referencing them will fail at runtime, not when you submit them, which is a massive headache. Second, namespace isolation is your best friend for resource boundaries. You've got to use resource quotas to stop one user from accidentally hogging all the GPUs. And lastly, the docs might show you a cute, simple port forward to access the dashboard locally, but for real production, you need to expose the API through an ingress with TLS for proper security. No shortcuts there.
It's also super important to understand the licensing tiers. Polyaxon gives us an open-source community edition, and that covers the entire core workflow we've discussed today. Submitting jobs, tracking, tuning, all of that is totally free. However, if your organization demands features like role-based access control, single sign-on, or heavy-duty advanced audit logging, those require upgrading to the Managed Polyaxon Cloud or the On-Prem Enterprise Edition.
Let's wrap up with the real-world limitations, because there's always a catch, right? Polyaxon has a very real, steep learning curve. The YAML schemas for complex workflows like directed acyclic graphs or matrix searches are really extensive. Your team absolutely needs deep Kubernetes experience to maintain this beast. To put that into perspective, while there's an awesome Slack community with around 1,500 folks, if you hit a weird edge case that isn't in the docs, you're probably going to find yourself reading the raw source code to figure it out. Teams without strong K8s experience will spend way more time wrestling with infrastructure before they even get to do any actual machine learning.
Which brings us to our final thought for today. We've seen exactly how Polyaxon can end the dreaded GPU chaos by turning compute into a heavily managed, tracked, and auditable resource. But it demands serious technical rigor to deploy and maintain. So I leave you with this question to chew on. Is your team ready to trade that steep Kubernetes learning curve for ultimate infrastructure control? Think about it. Thank you so much for joining me for this explainer. I really hope this deep dive into Polyaxon gave you the structured insights you needed. Keep learning, and I'll see you next time.